Right then, so we've talked about u substitution and integration by parts, and for the most part those are pretty helpful. But next up we need to discuss a more specific topic, the topic of integrals that have to do with trigonometric functions. Because these can get pretty weird and a little bit difficult to handle. Okay. So let's look at an example here, first of all, just to sort of illustrate how weird this can get. So let's say we were asked to evaluate the indefinite integral of secant x dx. How would you do that? Well, let's see here. It's definitely not secant x tangent x, because that's the derivative. What we're looking for would be the antiderivative of that. So how would you do this? Well, sometimes it's a good idea to break down a trigonometric function into terms of sines and cosines, and we can do that here. We can say secant x is the same as 1 over cosine x, because it is. That's the definition of secant, right? But I don't think that helps us, because it's not like you can do a u substitution on that, or an integration by parts on that. So what do? Well, this is at least one way of doing it. What I'm going to do is I'm going to take the integrand here, and I'm going to multiply it by 1. A really weird way of writing 1. Okay? And that really weird way of writing 1 that I'm going to select is secant x plus tangent x divided by secant x plus tangent x. You might be wondering why this, and that's a valid question. But first, can we just recognize that this actually works, right? This is 1, right? Because it's just something divided by itself. So it is 1, and we can do this, right? Okay. So now at this point, let's try distributing that secant x through to these two things. So we get secant squared x plus secant x tangent x. All of this is divided by secant x plus tangent x dx. All right, so I guess so, right? But at this point, you look at this and you're like, I don't see how this is easier than this. But it is, okay? It is, because now we can do a u substitution on this. What I'm going to do is I'm going to say u equals secant x plus tangent x. Okay? In other words, the denominator, right? Well, if we do that, then we have to figure out du. So let's see, that's going to be secant x tangent x plus secant squared x dx. Does that look familiar? That's exactly what we have on top here, right? Okay. So this whole thing can just turn into the indefinite integral of 1 over u du. And then, of course, the antiderivative of 1 over u is just ln, absolute value of u, plus c. And then u is just a name for secant x plus tangent x. So that means that this is no more than the natural log of the absolute value of secant x plus tangent x plus c. Okay? So I started us off with this one because first of all, it shows you how weird this can get with trigonometric functions, but also because it's kind of in a class by itself. Like, you don't really use a technique that's quite like this for any other function than secant, except cosecant. For cosecant, rather than multiplying by secant plus tangent over itself, what you do is you multiply by cosecant plus cotangent over itself, and then you go from there. But apart from those two, I can't think of anything else where this exact thing is helpful. Okay? But you should know how to do this, so we did it. Okay? Now, okay, so that takes care of how you would figure out the antiderivative of secant x or cosecant x. Now, let's see what would happen if we were to deal with just a slightly different situation. Well, actually, completely different. So, let's suppose you were given an integral that looks like sine to the m of x times cosine to the n of x dx. And assuming here that m and n are non-negative integers. I guess that's not really a question, that's a statement. M and n are non-negative integers. Okay. Well, what you'll do in this case will really depend on which, if either, of m and n are even or odd. Okay? So we have three cases to consider. Case one is that n is odd in that case, what you're going to end up doing is you're going to separate out all of the factors of cosine here except for one of them, and then you'll have an even number of those. Then you can use cosine squared plus sine squared equals 1 to turn those into terms of sines, and then you can use u substitution from there. Let's talk about how that's done. So first of all, if n is odd, then that literally just means that n is equal to 2k plus 1 for some integer k. Right? 3 is an odd number because it's 2 times 1 plus 1. And 15 is an odd number because it's 2 times 7 plus 1. And 0 is an odd number because it's 2 times 0 plus 1. Wait, did I say 0 is an odd number? I meant to say 1 is an odd number because it's 2 times 0 plus 1. Negative 3 is an odd number because it's 2 times negative 2 plus 1, and so on. You get the idea. Okay? So every odd number is 2 times some other integer plus 1. Right? In that case, what we are looking at here is the integral of sine to the mx times cosine to the 2k plus 1 x dx. Right? Because if n really is 2k plus 1, then we can just replace this exponent. Fine. Now, if you have addition in the exponents, that's the same as having a product of two exponentials. So we can understand this as the integral of sine to the m of x times cosine to the 2k of x times cosine to the 1 of x dx. And of course, cosine to the 1 is just cosine. Now then, cosine to the 2k, well, if we have multiplication in the exponents, that's the same as taking the exponents sequentially. So then this is the same as the integral of sine to the m of x times cosine squared x raised to the k times cosine x dx. Okay? Right? Because if we have these exponents sequentially with parentheses and such, then that's the same as multiplying the exponents, right? Now then, cosine squared. Well, if cosine squared plus sine squared equals 1, then that would mean that cosine squared x is the same as 1 minus sine squared x. In that case, what we are looking at here can be written as the integral of sine to the m of x times 1 minus sine squared x to the k times cosine x dx. Now at this point, if you say u equals sine x, then du ends up being cosine x dx, in which case this just becomes the integral of u to the m times 1 minus u squared to the k du. Okay? And now this, of course, is a polynomial. Maybe you might need to do some distribution or whatever to get the integral to work out nicely, but it's just a polynomial. So ultimately the power rule will be able to be used in some way on it, and so that will handle the problem. Okay? Let's look at an example where this sort of thing happens. I think it's always more helpful to work with examples than just to talk about things in the abstract. I guess it depends on the level of math we're talking about, but definitely for calculus, I would say do lots of examples. So let's say we're given the indefinite integral of sine to the fourth x cosine to the fifth x dx. Okay? And this is case 1 because n is odd, right? So what we're told to do is first of all understand 5 as being 2k plus 1 for some appropriate integer k. That integer would have to be 2 because 5 is 2 times 2 plus 1. In that case, this can be rewritten as the integral of the sine to the fourth x cosine of 2 times 2 plus 1 x dx. Now, just as before, we can separate out one factor of cosine x, and the rest of this is an even power of cosine, which means we can write it as cosine squared raised to something else. In this case, that something is 2. So we can write this same thing as the integral of sine to the fourth x times cosine squared x squared times cosine x dx. Now from here, once again, we can say cosine squared is the same as 1 minus sine squared, which means this turns into the integral of sine to the fourth x times 1 minus sine squared x squared times cosine x dx. Right? Now from here we can use u substitution. U is going to be sine x, in which case du ends up being cosine x dx. So then this becomes the integral of u to the fourth times 1 minus u squared squared du. Okay? And as I said, this is just a polynomial. It's a rather unsightly way to write a polynomial, but it is just a polynomial. We will now, I suppose the best thing to do next would be to go ahead and distribute all of this. So we have u to the fourth times 1 minus 2u squared plus u to the fourth du. This now becomes the integral of u to the fourth minus minus 2u to the 6th plus u to the 8th du. And you can take that antiderivative by just doing the power rule. So this becomes 1/5 u to the 5th minus 2/7 u to the 7th plus 1/9 u to the 9th plus c. And from here, we just need to say u is just a name for sine x. So now this becomes 1/5 sine to the 5th x minus 2/7 sine to the 7th of x plus 1/9 sine to the 9th of x plus c. And that is our indefinite integral. Okay? So that's at least what you can do if n is odd. And this will always work if n is odd. Well, okay, so yeah, there's more we should say though. So the next issue is, well, perhaps instead n is even. So let's say here, case 2. Case 2 is that n is even. And let's say m is odd. Alright? So now, of course, we've dealt with the case where n is odd, but now if we're saying n is even and m is odd, then case 3 is going to have to be that they're both even, right? And yes, we'll get to that. But for right now, let's say n is even, m is odd. Okay? In that case, we can say m is equal to 2l plus 1 for some appropriate integer l. Right? For the same reason, you could say n was 2k plus 1 before. We can say m is 2l plus 1. In that case, we can play the same game. We can say, all right, this is going to be the integral of sine to the 2l plus 1 of x cosine to the n of x dx. And now what I'm going to do is I'm going to apply the same sort of strategy. I want to separate out one factor of sine and then write the rest of those factors as sine squared raised to some power. So this is going to end up being the integral of sine squared x raised to the L times cosine to the n of x times the sine of x dx. Right? Just separating out one factor of sine. The rest of this is an even power. Multiplication in the exponent means taking the exponents sequentially. All right, in that case, once again, we can say sine squared is just 1 minus cosine squared, in which case this will become 1 minus cosine squared x raised to the L times cosine to the n of x times sine x dx. And now from here, once again, we can use u substitution. We can say u equals cosine x, and then du equals negative sine x dx, in which case this becomes the integral of 1 minus u squared, 1 minus u squared raised to the L times u to the n times negative du, so obviously we can put the negative sign outside. Okay? And then, you know, again, this is just a polynomial and you can handle it in a similar sort of way, right? So there's not really much different there, but just for the hell of it, I guess we'll do one example of such a problem. So let's say this is now, instead of sine to the fourth cosine to the fifth, it is sine cubed cosine to the fourth. Now then, once again, we can say 3, which is an odd number, is 2 times 1 plus 1. That means that this is the same as sine raised to the 2 times 1 plus 1 of x cosine to the fourth of x dx. Once again, we can factor out one sine, so we get sine squared x raised to the 1 cosine to the fourth x sine x dx. Now, of course, sine squared x raised to the 1 is just sine squared x. So, and of course, sine squared is 1 minus cosine squared, which means that this is just 1 minus cosine squared x times cosine to the fourth x sine x dx. In which case, once again, u equals cosine x, so now du equals negative sine x dx. In that case, what we get here is going to be, well, it's going to be negative integral of 1 minus u squared times u to the fourth du. We can distribute that, and what we'll get here is integral of, let's see, u to the sixth minus u to the fourth du. And by the way, what I've done here is I've gotten rid of this negative sign by just switching the position of these two terms. So then, of course, we can take the antiderivative of this by the power rule. So what we get is 1/7 u to the seventh minus 1/5 u to the fifth plus c. In which case, what we're looking at has to be 1/7 cosine to the seventh of x minus 1/5 cosine to the fifth of x plus c. And so that becomes our indefinite integral. All right, and so finally we have case 3. Case 3 is that neither of these two integers is odd. So they're both even, in other words. So case 3, m and n are odd. I mean even. Even. If they're both odd, then obviously case 1 could apply. But yes, let's say they're both even. All right, in this case, what we're dealing with, well, we can say m is equal to 2k and n is equal to 2l for some integers k and l. Right? That's what it means to be an even integer. It just means that it's divisible by 2, or in other words, 2 times some other integer, right? Now then, if that's the case, then what we're dealing with is actually the integral of the sine to the 2k x cosine to the 2l x dx. And so now that can be rewritten as integral of sine squared x raised to the raised to the k times cosine squared x raised to the L dx. I just realized I might have. So in this case, I've been associating k with m and L with n. I might have switched that from the previous case. So if I did that, sorry about that. But at least the cases are consistent. In any case, so what we have is this. From here, we can use trigonometric identities. Okay? We could be using any or all of the following. Perhaps we'll be using that sine squared x equals 1/2 1 minus cosine of 2x. Perhaps it's cosine squared x that we'll say is 1/2 1 plus the cosine of 2x. And perhaps it is the fact that sine x cosine x can be understood as 1/2 sine of 2x. Okay. So now, the solution is not as clear-cut as it was in the previous cases, because it just might depend. And also, depending on how large k and L are, this could go on for a long time. But at least these are some things that we can use if we get, stuck. So, of course, this definitely demands that we do some examples. Right, so how about this one? The integral from 0 to pi of sine squared t cosine to the 4th t dt. Right, so this is case 3 because 2 and 4 are both even, right? Now, I guess what I really want to do here is, the first thing I want to do is group together two factors of sine and two factors of cosine. So I can say that this is sine t cosine t squared multiplied by cosine squared t dt. Okay, and we can do that, right? So now I suppose sine x cosine x is 1/2 sine 2x, so perhaps that will be useful here. So we'll say this is the integral from 0 to pi of 1/2 sine of 2t squared times, okay, and meanwhile cosine squared we can understand as 1/2 1 plus cosine 2t. dt. Now from here we can distribute. Okay, we've got some stuff that we can distribute. So first of all, 1/2 squared is going to be 1/4. And then 1/4 times 1/2 is just going to be 1/8. We can pull that outside, so I'm just going to have a 1/8 outside. And then this is the integral from 0 to pi of, let's see here, this is going to be sine squared of 2t multiplied by, let's see here, this is going to be 1 plus the cosine of 2t dt. So from here, we can distribute. We can say this is 1/8 integral from 0 to pi of sine squared of 2t plus sine squared of 2t times cosine of 2t dt. So now at this point, we've reduced the problem to figuring out two different integrals that are easier. We can figure out this integral and this integral, we're done. Just multiply them by 1/8 and add them together. This one can be done through u substitution. Okay? We just need to say u equals sine 2t. And then du will be 2 cosine 2t dt, which will absorb this part, and then we'll just have 2 times the integral, no, 1/2 times the integral of u squared du. Fine. As for this one is a little bit different, okay? Because this is also what we would call case 3, because it's sine to an even power times cosine to the 0, which, of course, 0 is even. So then, to figure out this part, the second term here, is not the issue. The harder part would be figuring out this first term. So why don't we just take a moment to figure that out. Let's see, so we have the integral of sine squared of 2t dt from 0 to pi. And, you know, there's a constant outside, and of course there's more stuff added to it, but that's fine. We can handle that. This is the hard part. So at this point, what we can say is, well, sine squared of 2t, that's the same as 1/2, 1 minus the cosine of 4t. So now this can become integral from 0 to pi of 1/2 times 1 minus the cosine of 4t dt. So now from here, of course, we can pull out the 1/2. So we get 1/2 integral from 0 to pi of 1 minus cosine of 4t dt. And the rest should be not too hard to handle, right? Antiderivative of 1 is just t. Antiderivative of cosine of 4t is going to be 1/2 sine of 4t, which you can find by doing a u substitution, u equals 4t. So this just becomes 1/2 times t minus 1/4 sine of 4t, evaluated from 0 to pi. And so this becomes 1/2, let's see, whatever, pi. Now, minus 1/4 sine of 4 pi. Sine of 4 pi is 0, just as the sine of any integer times pi is 0. Now, minus 1/2 0 minus 1/4 the sine of 0, which is also 0. And so we just get pi over 2. Okay? That's this part. Okay? Of course, as I said, there's this part to handle, but hopefully you can do that on your own. Okay? And if not, it's in the notes. Right then, so next up, we need to consider a similar but different type of situation. We've dealt with situations where we have a power of sine times a power of cosine. What if we were to have a power of tangent times a power of secant? So now, suppose we're given an integral of tangent to the m of x, secant to the n of x dx, where once again, m and n are non-negative integers. So m and n are non-negative integers. Okay. Once again, this is going to depend on which of these are even and which are odd. All right? So our case 1 is going to be that n is even. In the previous example, the case 1 was that n was odd. Here, case 1 is that n is even. This one is going to be the easier one to deal with. So case 1, n is even. All right, if n is even, then that would mean that n has to be equal to 2k for some integer k. That's what it means to be even. In that case, what we're looking at here is the integral of tangent to the m of x times secant to the 2k of x dx. All right, so now let's separate out not one but two factors of secant from this. Okay. Actually, I guess if k happens to be 0, then that doesn't make a lot of sense. Okay, so let's say k is greater than 1, in which case n is even and greater than or equal to 2. But in any case, yes, we'll take out two factors of secant from here. So what we'll do is we'll say this is integral of tangent to the m of x secant to the 2 times k minus 1 x secant squared x dx. And if you add the exponents here, you should get back to this, right? Now then, secant to the 2 times k minus 1. That can be understood as secant squared raised to the k minus 1 power. So this is the integral of tangent to the m of x times secant squared x to the k minus 1 times secant squared x dx. All right? Next up, secant squared can be understood as tangent squared plus 1. That means that this can be rewritten as integral of tangent to the m of x times tangent squared plus 1 raised to the k minus 1 times secant squared x dx. In which case, we can do a u substitution now. We can say u equals tangent x. In that case, du equals secant squared x dx. And so this becomes integral of u to the m times u squared plus 1 to the k minus 1 du. And once again, there's some stuff that you need to do with that, of course. But it's a polynomial, okay? And ultimately, you know how to figure out the antiderivative of a polynomial. Yeah, there might be some distribution involved, but it's not something you can't handle. So let's do an example of this. Let's suppose we're given the integral of tangent squared theta secant to the 4th theta d theta. Right then, so just as in our abstract discussion, we're going to leave the tangent alone, and we're going to separate out two factors of secant theta. And then that leaves two factors remaining. In this case, what we've called k is actually 2. Now, those remaining factors can be understood as tangent squared theta plus 1 raised to however many, whatever k minus 1 is. In this case, it's just 1, so whatever. And then we still have secant squared theta d theta. Now, if we say u equals tangent theta, then du ends up being secant squared theta d theta. In that case, this becomes the integral of u squared times u squared plus 1 du. Now, of course, that is just the integral of u to the fourth plus u squared du. And you know how to do that, right? That would just be 1/5 u to the fifth plus 1/3 u to the third plus c. And as we said, u is just a name for tangent theta, so this is the same as 1/5 tangent to the fifth theta plus 1/3 tangent to the third theta plus c. And that is our indefinite integral. All right? So that handles the case where n is even. Now then, the next case that we're going to consider is that m is odd and n is greater than or equal to 1. So this is case 2. M is odd and n is greater than or equal to 1. So n is a positive integer. In that case, of course, m is equal to 2l plus 1 for some appropriate integer l. In which case, what we're looking at here becomes the integral of tangent to the 2l plus 1 of x times secant to the n of x dx. Now, what we're going to do is we're going to, once again, we're going to take out one factor of tangent here, and then the rest of this is going to be tangent squared raised to a power. So let's do that first. So this is the integral of tangent squared x raised to the nth power times secant to the n of x times tangent of x dx. And the next thing we're going to do is we're going to take exactly 1 power of secant, which we can do because n is greater than or equal to 1, and separate that out too. So what we're going to get here is integral of tangent squared x to the L, secant to the n minus 1 of x, secant x tangent x dx. All right, so now at this point we can do u substitution. Well, actually, one more thing before we do u substitution. Tangent squared x can be understood as secant squared x minus 1. So first of all, let's write that. So this is going to be the integral of secant squared x minus 1 raised to the L, secant to the n minus 1 of x, secant x tangent x dx. So now, as I said, u substitution works here. We can say u equals secant x and du equals secant x tangent x dx. In that case, what we're looking at here will become integral of u squared minus 1 raised to the L times u to the n minus 1 du. And that, once again, is a polynomial, which you can handle. So let's do an example of that. Let's see here. Okay. Right, so then what we're going to have here is tangent to the fifth x times secant to the third x dx. Okay, and this falls into our case 2 because m, which is 5, is odd, and n, which is 3, is greater than or equal to 1. So what we'll do is we'll take out 1 power of tangent and 1 power of secant. So what we'll get here is tangent to the fourth theta times secant squared theta times secant theta times tangent theta d theta. Then tangent to the fourth can be understood as tangent squared squared. Tangent squared is the same as secant squared minus 1. So this is the same thing as integral of secant squared theta minus 1 squared secant squared theta secant theta tangent theta d theta. Now from here, if we say just that u equals secant theta, then du ends up being secant theta tangent theta d theta, in which case what we're looking at here becomes the integral of, let's see here, u squared minus 1 squared times u squared du. And then we can distribute. So this becomes integral of u to the fourth minus 2u squared plus 1 times u squared du, which in turn turns into integral of u to the sixth minus 2u to the fourth plus u squared du. You can take the antiderivative of that and get 1/7 u to the seventh minus 2/5 u to the fifth plus 1/3 u to the third plus c. And then finally, u is just a name for secant theta, so this becomes 1/7 secant to the seventh of theta minus 2/5 secant to the fifth of theta plus 1/3 secant to the third of theta plus c. And that will be our indefinite integral. Okay? Okay, so now you're probably expecting here for there to be more cases, right? Cases that don't cover what the previous cases handled? No. So in the case of sine to the m, cosine to the n, you had 3 cases and those covered all the possibilities, right? For this one, it's just not so easy, okay? If it so happens that your m and n do not fall into either case, you're just gonna have to get creative. You're just gonna have to try something and see what happens, okay? So why don't we take a minute to talk about an example which is really weird, one of the weirdest, I'd say. But you ought to see it just as part of taking calculus 2. So this one's going to be secant cubed x dx. All right, well, let's see here. First of all, it's not either of those two cases, because we can understand this as being tangent to the 0 of x times secant cubed x dx, but it's not gonna help, right? Because we can't separate out two factors of secant and then get a power of secant squared remaining. And also we have no tangents to deal with. So what do you have to do here? Well, this one is really weird, as I said. Weird enough that you should see it and you should understand what's going on, but it's going to be harder than something that you would get on like a quiz or a test. So if you watch this and you are thinking, I don't know if I could do this myself, that's okay. I just need you to understand what's going on and see this and understand that it can be done. But to do it yourself on a quiz or a test, probably not going to be that, well, probably not going to ask that much of you. So here's what we do. This one we're going to do by integration by parts. We're going to say u equals secant x and dv equals secant squared x dx. Now if you do this, then du ends up being secant x tangent x dx, and v has to be tangent x. So now, as always, integration by parts formula applies. It's going to be uv minus the integral of v du. So this is going to be secant x tangent x minus the integral of, let's see here, this is going to be tangent squared x secant x dx. All right, well, that's another one that doesn't fall into either case, right? Because this the power on secant is 1, it's not even. And also, well, it doesn't fall into the other case either. Whatever. So, what are we going to do here? Well, here's something we can do. We can say tangent squared is the same as secant squared minus 1. We can say that the integral of secant cubed x dx is going to be equal to secant x tangent x minus the integral of, let's see here, secant squared x minus 1 times secant x dx. Gonna get a new marker. This one's seeming to run out. And then you can distribute that. So then this becomes secant x tangent x minus the integral of secant cubed x minus secant x dx. All right, well, from here, I suppose you could split this integral among these terms. So then you can write this as secant x tangent x minus the integral of secant cubed x dx plus the integral of secant x dx. And by the way, this is all equal to the integral of secant cubed x dx. do you notice something here? Do you notice that this is just the negative of that? So that means you can just add this to both sides and get twice that on the left, which means that we can write this as 2 times the integral of secant cubed x dx equals, let's see here, this is going to be secant x tangent x plus the integral of secant x dx. So now from here, integral of secant x, we happen to do that at the beginning of class today. So this turns into 2 integral of secant cubed x dx. This becomes secant x tangent x plus, as we saw earlier today, the natural log of the absolute value of secant x plus tangent x plus c, and then just divide both sides by 2. So then the integral of secant cubed x dx ends up being 1/2 secant x tangent x plus 1/2 natural log of the absolute value of secant x plus tangent x plus c. And that's it. Okay. So what is this trying to illustrate? Well, what I'm trying to illustrate with this example is that if you get an integral that is a power of secant times the power of tangent, or other way around, doesn't matter, and it doesn't fall into either case, you probably can do it, but it might be painful. Okay? Also, in case anyone is wondering why this says c and not c over 2, it's because, like we said before, in a previous example, if you take c and you divide it by, do something like divide it by 2, then it's still just a constant, right? It still could be any constant whatsoever, so there's no real point in saying c over 2. If you want to be very precise, I guess you could give this a different name. You could call it something like C1. That's fine. But you don't have to. All right? So, that is the lecture for today. Now, about the homework. It's up now. And I've recently decided, based on some feedback that I received from you guys, that I should only do odd-numbered problems from now on. The reason why is because if I do odd-numbered problems, then you can check your answers at the back of the book in one of the appendices. Okay, so that way you know whether you get it right when you're actually done. Okay, and so I'll direct you to that. Go ahead and get some practice.